this talk, I'm going to discuss intuitionistic grammar logics, which were introduced in the short paper published in CLAR 2021, and which are a basic generalization of intuitionistic modal logics and intuitionistic tense logics. Essentially, what they do is take a special class of multimodal logics called grammar logics and put them on an intuitionistic footing as opposed to a classical footing. So just a quick overview of the talk. What I'm going to do next is give an introduction to classical grammar logics, explaining the type of logics that they subsume and why they're useful. Then talk about intuitionistic logic. And then after that, talk about how to fuse these two together to get intuitionistic grammar logics, as well as what the benefits of this are. Then I'll introduce these logics, talking about their semantics and axiomatizations, and end by discussing some potential future work. So what are classical grammar logics? Well, these are multimodal logics, which extend classical propositional logics. They have propositional atoms, positive ones and negative ones, disjunction and conjunction, and you extend with two different types of modalities, necessity modalities and diamond modalities. And these are indexed with characters, or a character X, among, or which varies among, an alphabet. Now, the thing is that inside of your associated Kripke models, you have accessibility relations which are indexed with these characters. And when you have sequences of these accessibility relations, these correspond to strings or words which can be generated from a formal grammar. So when these logics were first introduced and discussed in the 1980s, equivalences were shown between the satisfiability problem of formulae in grammar logics and the ability to generate a word from a given formal grammar. And this is where the name grammar logic comes from. Now, these logics subsume a variety of different classes of logics that have various different purposes and uses. For example, certain epistemic logics, which are used for reasoning about knowledge, can be seen as types of grammar logics. So to give an example of an epistemic sentence which is expressible in our language, this says, for example, that if Bertrand Russell knows that the King of France is bald, then it follows that the King of France is bald. So this is an instance of the so-called factivity axiom, which appears in certain epistemic logics. So these are this is one use of grammar logics, or one subclass that is subsumed by them. Another is temporal logics, which are used for reasoning about time. For example, if this is a sentence which is expressible in our language. It says that if it's not the case, if at every point in the future the sun shines, then at some point in the future it is not the case that the sun shines. So these, of course, are quite useful in verification, for example, and in model checking. Also, certain description logics, such as ALC, the attributive concept language, can be seen as subclasses of grammar logics. These are used in knowledge representation, for example, in the construction of ontologies or databases, where you might want to query them, obtaining, for example, implicit knowledge on the basis of explicitly given knowledge. So here's an example of a description logic sentence in our given formalism. It says that if someone is the parent of a human, then they themselves are human. And here is an example of what that sentence would be in description logic notation. So we have a variety of different kinds of logics with various purposes that are subsumed by grammar logics. This is one of the reasons why this class is interesting. But as I said before, in the paper what I do is I remove the classical and classical grammar logics and replace it with intuitionistic to put it on an intuitionistic footing. Now, for those who aren't familiar, intuitionistic logic was essentially introduced in the early 20th century and is based on the intuitionist philosophy of L.E.J. Brouwer. In this philosophy of mathematics, Brouwer rejected the law of the excluded middle on certain philosophical grounds, and the consequence of this was that one obtains a form of reasoning or logic which is constructive. What does that mean? Well, one of the defining characteristics of constructive reasoning is that if one is able to prove an existence claim, then it follows that from that proof you have a witness, a concrete witness showing that this particular object exists, or you have an algorithm for the object's construction. So to make this a bit more precise, I'm going to give an example showing how to prove a theorem by making use of non-constructive reasoning. And therefore, by contrast, this will give an idea about what constructive reasoning is. Now, what this theorem states is that there exist two irrational numbers such that one to the power of the other is a rational number. So how can we prove this theorem? Well, let's give a non-constructive proof. Let's take, for example, the square root of 2. We know that it's irrational. And now by the law of the excluded middle, we know that square root of 2 to the square root of 2 is either rational or it's not, meaning it's irrational. So in the first case, if square root of 2 to the square root of 2 is rational, then we have something which witnesses the truth of this theorem. And since square root of 2 is itself an irrational number. Now in the second case, let us suppose that it is irrational. If that's the case, we can take this irrational number and we can raise it to the power of the square root of 2. And this is equal to the number 2, which is a rational number. So regardless of which case holds, we know that we have two irrational numbers such that one to the power of the other gives a rational number. Now, what is the problem with this? Well, the problem with this approach is that we don't obtain a singular example of two irrational numbers such that one to the power of the other gives us a rational number. Instead, we have a set of possibilities, and the proof doesn't tell us which one is the case. Now, if this proof was constructive, it would, or it would provide, again, an algorithm that allowed us to construct these two irrational numbers which satisfy this theorem. So intuitionistic logic has had a variety of applications in computer science and also in the foundations of mathematics, which is one of the reasons why people have been interested in it. Now, in the 1980s, due to the interest in modal logic and also intuitionistic logic, researchers began to put these two together. So having logics which perform both modal reasoning about possibility and necessity while at the same time having these constructive aspects. And these intuitionistic modal logics were found to have various applications, for example, in verification, in reasoning about functional programs, and also in defining certain programming languages. Now, for me, the reason why I undertook this project is because there are various open problems concerning intuitionistic modal and tense logics, and so I generalized the class of these logics to intuitionistic grammar logics to try to solve these problems in a very general way. So there are open problems concerning the construction of proof systems for certain classes of these logics. Also, very few intuitionistic modal logics are known to be decidable, so there's a lot of decidability questions which are still open, which I can use proof theory for, and also interpolation is something that, to the best of my knowledge, is open for in certain intuitionistic modal and tense logics, as well as the intuitionistic grammar logics. So again, my goal with this project was just to define intuitionistic grammar logics with the goal of developing proof systems for them, and then solving decidability and interpolation problems. But perhaps there are also practical applications that one might find as well for intuitionistic grammar logics. Okay, so what are these logics? Well, intuitionistic grammar logics are defined, first of all, relative to an alphabet sigma, where sigma can be partitioned into a set of what are called forward characters, such as A, B, and C, and a set of what are called backward characters, such as A bar, B bar, and C bar. And the forward characters and backward characters are converse to one another, or for example, A is the converse of A bar and vice versa. And I'll explain the significance of this in just a moment. First, let me introduce the language. The language that is used is a propositional language. So we have propositional atoms P, we have falsum, disjunction, conjunction, we have intuitionistic implication, we have diamond modalities, and we have box modalities. Now, if these modalities are indexed with forward characters, then they are referred to as forward modalities. And if they're indexed with backward characters, then they are referred to as backward modalities. Now, what forward modalities do is they talk about things being true in the future of a given crypto model. So for example, if I have A diamond A holding at a point in a model, then along the A accessibility relation, A will be true at some future point. And for example, if I have, say, A bar diamond A holding in a model, then there must be some point in the past where A holds. So again, this is just to give some intuition. Forward modalities speak about the future, backward modalities speak about the past, and you can see that these logics really are a generalization of intuitionistic tense logics. Okay, so now let's look at the semantics and models that are used. The semantics that's used here is a very basic generalization of the birelational semantics that's provided for both intuitionistic modal and tense logics. The types of models that I defined are called birelational sigma models, and to give an idea about what they are, I will now go through their various components. These are quadruples, where the first component, W, is a non-empty set of points called worlds, so W0, W1, W2, and W3, for example. We then have a binary relation, which is defined over the set of worlds, which is a pre-order, meaning it is reflexive and transitive. I've left the reflexive arrows implicit on this diagram, but just know that they're there. We then have a family of modal relations, which are indexed with characters from our alphabet, and this family must satisfy a constraint, namely, if I have an x relation going in one direction, I must have the converse of x going in the opposite direction, which again, remember that forward modalities speak about the future, and backward modalities speak about the past. So this is really encoding that property into these models, or our ability to express this in these models. We also have a valuation function which maps propositional atoms to worlds, meaning that they are true there. And this must satisfy a monotonicity condition with respect to the intuitionistic relation. So for example, if Q is mapped to W naught, then it must not only be true at W naught, but also at every point in the future of W naught. So for example, W2. Again, only along the intuitionistic relation. And you can see that's true of P as well. Now there are two further conditions which are imposed on these models. And essentially what these conditions do is they ensure that we not only have monotonicity with respect to propositional atoms, but also with respect to complex formulae. And if you're interested, there is in the paper references to the literature which provide philosophical justifications for why we want these conditions to be imposed. But I'll just quickly explain what they are or define them. So the first condition, called the forward condition, is a type of convergence condition. And what it says is that if in my birelational sigma model, if I have a point W naught that intuitionistically sees a point W2 and modally sees a point W1, then there must exist a point W3 which is modally seen by W2 and which is intuitionistically seen by W1. Sort of a forward simulation condition. And we have the backward condition, also a type of convergence condition, which says that if I have a point W1 which is modally seen by a point W naught and which intuitionistically sees a point W3, then there exists a point W2 which is intuitionistically seen via W naught and which modally sees W3. Okay, so that is the types of models that are used by relational sigma models. And now what I'm going to do is explain how the intuitionistic implication, diamond, and box modalities or connectives are interpreted in this setting, just because they have a somewhat complicated interpretation. So let's look at intuitionistic implication first. If A implies B is satisfied at a point, then this holds, if and only if, for every future point along the intuitionistic relation, if A holds there, then B holds there. That's what it means. So for example, I've given an example in the bottom half of the slide. If we're at W naught, then what are the future points of W naught? Well, W naught itself along the intuitionistic relation, which remember is reflexive, where Q holds, and also W2 where Q holds. So what this means is that at W naught, at every point in the future where top holds, which holds everywhere, Q holds. So top implies Q holds at W naught. Now let's look at X diamond. So X diamond A holds at a point W, given that there is a point in the future of W along the X relation such that A holds there. So for example, at W naught, we have a point W1, which is in the future of the X relation, where little r holds, and therefore, at W naught, X diamond R holds. Last, let's look at the X box relation. X box A holds at a point W, if and only if, whenever we can make a move along the intuitionistic relation, and then make a move along the modal relation, A holds there. So let's look at our example. Starting at W naught, I can move to W naught along the intuitionistic relation. Again, it's a reflexive relation, because it's a pre-order. And then I can make a modal move to W1, where P holds. But also I can make an intuitionistic move to W2 and a modal move to W3, where P holds. So regardless of how I make an intuitionistic move and then a modal move, P holds. This means that X box P holds at W naught. So this explains how these special connectives are interpreted in this setting over birelational sigma models. Now I defined a class of base logics called IKM, where M is a natural number. And each base logic IKM, where IKM stands for intuitionistic multimodal K, each of these can be axiomatized with the following set of axioms. The parameter M, by the way, is determined on the basis of your alphabet, but this is something explained in the paper. Now the axiomatization is obtained by taking intuitionistic propositional logic and extending with the following axioms and inference rule. And all this really is just taking the axiomatization for intuitionistic tense logic, given in a 1988 paper by Ewald, and putting it into a multimodal setting. And then what the paper does is it shows how to shows soundness and completeness of this axiomatization relative to birelational sigma models. In other words, the set of theorems that are generated by the axiomatization for IKM is equal to the set of validities that are determined on the basis of birelational sigma models. The paper also considers axiomatic extensions, so extensions of IKM with the so-called seriality axiom. If this is added to your axiomatization, then it becomes sounding complete relative to birelational sigma models, where your modal relation for x is serial, meaning that if, for any point, there's always an x point in the future. And also considers extensions with what are called intuitionistic path axioms, or more simply IPAs. I just use the term IPA because intuitionistic path axiom is quite a mouthful. So this class of axioms subsumes a lot of well-known or well-studied axioms that occur on the literature in modal logic. For example, the symmetry axiom is an instance of an IPA. If this is added to your axiomatization, then it becomes sound and complete relative to birelational sigma models, remember sigma again being your alphabet, where the modal relation RA is symmetric, so if one point sees another, then the vice versa must be true. The reverse must be true. And also, we have the reflexivity axiom as an instance of an IPA, which essentially ensures that your modal relation RA is reflexive inside of your birelational sigma model. Other axioms that are instances of IPAs include transitivity and Euclideanity. So, intuitionistic versions of S4, S5, for example, are all subsumed by the class of intuitionistic grammar logics. Okay, so just to conclude, what this paper does, it's a very basic goal that's achieved. It shows that taking an axiomatization for IKM, extending with whatever seriality axioms or whatever intuitionistic path axioms, it proves soundness and completeness for that axiomatization. Soundness is shown by a very basic induction argument on the length of given derivations. Completeness is a pretty standard canonical model construction. So what I would like to do now in future work, or what I have done, is provide nested sequence systems for the class of intuitionistic grammar logics, and then make use of these to write proof search procedures, which I'm in the process of doing, to identify decidable fragments thereof, and also to try to determine decidability for subclasses of these logics for which decidability is not known, for example, transitive intuitionistic modal logics, and also to make use of proof-theoretic methods of interpolation to show that these logics have the interpolation property, since this, to the best of my knowledge, is an open problem. So again, all of the work that I'm doing is of theoretical interest, but maybe, there are some practical applications for these logics as well that others might find. So thank you very much for your attention, and I hope you have a wonderful day.